Hey everyone, my name is Julius Collier. I'm in your class. I'm making this video because it seems like there's some confusion on the binomial distribution. So before we get into binomial, I think it's probably important that we know Bernoulli. Bernoulli was named after Jacob Bernoulli, the guy who I guess discovered it. It's not really a discovery, but a Bernoulli distribution is just an experiment with two outcomes, and at his it was 1 or 0. So probability of success, let's call that P, is going to be just P when x equals 1, and a failure is going to be when x equals 0. That's basically what the Bernoulli distribution is, just two outcomes. And binomial comes into play when you sum up sum up Bernoulli distributions. So let's give an easy example. Let's say you're shooting free throws. The probability of you making the shot is 80%. Let's call that P. P is 80%. Let's call Q 1 minus P. Q is failure. The probability of you missing the free throw is 100% minus 80%, which is 20%. So we have P as 80 and Q as 20. Now, what if I asked you, what is the probability of you making the first 2 free throws and missing the next 3? Well, we know how to do that. For you, making the first 2 is going to be 80% times 80%, and then missing the next 3 times 20% times 20% times 20%. Whatever that is, that's the probability. But what if I asked you, what is the probability of you making 2 free throws of 5 shots? Then you're gonna need to first you're gonna need to count. So you're gonna need to find out how many ways you can make 2 out of 5 free throws, and that's where combinations come in. And I think I've replied to a lot of people how to find combinations. You can easily just go to your TI-80 calculator, or simply, let's say you have n trials. In our case, it was 5, and the number of successes, let's call R. In our case, it was 2 successes. You can easily do n factorial divided by r factorial times in quantity n minus r, that whole thing factorial. Or you can just simply go to your TI-84 calculator. Now back to binomial. After you counted the amount of ways for you to, let's see, I said n and r. So n choose r. So in our case, n was 5 shots and r was 2 made shots out of the 5. So 5 choose 2. You're gonna have to multiply that times the probability of success to the amount of times you had a success. So in our case, the probability of success was 80%, and you're gonna take that to the power of 2, because we had 2, we're trying to count 2 successes. You're gonna multiply that times the amount of failures and the remaining trials. So the probability of the failure was 20. So you multiply that times 20%, and that 20% to the power of 3. We had 2 successes since it's 5 trials. 5 minus 2 is 3. So that probability would be n choose r times p to the r times q to the n minus r. And that's the binomial distribution. And there was a lot of confusion of setting it up in the calculator. And before I get to that, and keep in mind that the binomial distribution is discrete. Right now we're in discrete, but I'm gonna show you a continuous really fast to just show you the difference, and hopefully it helps out a lot. So I drew this out earlier. This is a normal bell curve, and it's continuous, as you can see. And the difference between continuous and discrete is discrete, you can count it, but continuous, you have to measure it. Like let's say I'm measuring heights of everyone in a classroom. It has to be continuous. Let's say these are the heights. 1 feet tall, 5 feet tall, 10 feet tall. Has to be continuous. What if I ask you the probability that someone in the classroom was exactly 5 feet tall? Well, that probability will be 0. And to make that make more sense, think of you at a bus stop. You're at a bus stop. You know that the bus comes between 8 and 8:05 p.m. If you're trying to ask yourself, what is the probability that the bus comes exactly at 8:01 p.m.? Well, that's virtually 0, because there's an infinite amount of time between 8 o'clock and 8:05 p.m. I hope that makes sense. And to make that easier, let's say you wanted to find the probability of the bus coming between 8 and 8:05 p.m. That's 100%, right? Because you know for sure it's going to come between 8 and 8:05 p.m. And to make it simpler, between 8 and 8:02 p.m. will be 50%. So in continuous case, to get probabilities, most of the time it has to be in intervals. You can't get an exact value. It's going to be virtually zero, because there are so many other, there are infinite amount of points between two instances. I hope that makes sense for continuous. Now, and I hope reading the notes, you know that the sum of probabilities must be 1. So the area under this curve for the entire curve is going to be equal to 100%. That being said, the probability that x is less than or equal to 10, we see that the entire space is 10 or below. We know for sure that's going to be 100%. And I split it up into 2. On the left side of 7, it's 75% of the probability, and on the right side is 25%. So the probability that x is less than or equal to 7 is 75%. And vice versa, on the other side, when x is greater than 7, it's 25%. Let me zoom that out. And now that we know that x less than 7 is 75, x greater than 7 is 25%, we can easily write this. We know that 100% minus 75% is 25%. Well, let's substitute for this 75% that we have up here. 100% minus the probability that x is less than or equal to 7%, we know that's going to be 25%. And 25% is the same thing as the probability that x is greater than 7. And then looking at the graph, that makes sense. This entire thing is 100%. If we take 100% and we take out this part, we're going to be left with 25%. So that's 100% minus the probability that x is less than 7 is going to be equal to the probability that x is greater than 7. I hope that makes sense in a continuous case. And a lot of the confusion came in a discrete case when setting up for the binomial in our calculators. Let me try to even that up. There we go. Hope this helps. So for now, ignore this. Let's look at a discrete case. I made a nice easy graph. Now it goes up to 7. And we see that the median and mean, since it looks perfectly symmetrical, and the mode is 4. And that's going to be at 40%. And if you add these up, it is going to be 100%. 40% plus 20 plus 20 plus 8 plus 8 plus 2% plus 2% is going to be 100%. Now, let's go through the probabilities once more. Let me get a pen to point this out. Okay, there we go. Now, the probability that x is less than or equal to 7, this is the cumulative distribution of this entire thing. You're going to accumulate every x less than or equal to 7. So you're going to accumulate 7, 6, 5, 4, 3, 2, and 1. So if you accumulate all of that, I said before that probabilities have to be 100%, and you can check the math, it is going to be 100%. Move my hand out the way. Now for the next one, the probability that x is greater than or equal to 4. So we're going to go to 4, and we're going to include 4 and have everything greater than or equal to 4. So we're going to add up 4 plus 5 plus 6 plus 7. So that's going to be 40% plus 20% plus 8% plus 2%. Did the math, and it's 70%. Now, on the other side, first we had the probability that x is greater than or equal to 4. Now, let's do the opposite, the other side. X is less than 4. So first we did 4, we included 4, and we went to the right. Now we're going to be at 4, we're going to exclude 4 and go to the left, because that's what's left over, right? And 100, the last one was 70%. 100 minus 70% should be 30%. So let's check that out. X is less than 4 is the same thing as x is less than or equal to 3. Since this is not continuous, we don't care, we're not including 4, we don't care about this space. There's nothing here. All we need is 3, 2, and 1. So the probability that x is less than 4 is the same thing as the probability that x is less than or equal to 3, which is 3 plus 2 plus 1. So 20% plus 8% plus 2% is going to give us 30%. 100% minus 70%. And let's put that down here. 100% minus 70% is going to equal 30%. Now let's substitute the 70%. 100% minus x is greater than or equal to 4. So that's 100% minus x then is greater than or equal to 4. It's going to be equal to x then is less than 4, which is going to equal to the probability of x is less than or equal to 3. And the reason why I wrote this is because this is what we need for the binomial distribution CDF. So for binom CDF, you need to put everything in x is less than or equal to the amount of successes that you're trying to get. And that's very important. And let's go down here. This is where our dilemma comes in. Sometimes the problem asks us to find, sorry about that. Sometimes the problem asks us to simply find the probability that x is less than or equal to 3. Well, that's simple. We can just go in our calculator and put in binomial CDF and put it in for 3. But on other times, as we've seen, it says x is greater than or equal to 4. Well, that is not in this form, so we need to rewrite it. And then that's where this comes in. 100% minus 30%. Remember that 30% was a less than or equal to 3. So 100% minus 30% is the same thing as 70%. And we know that 70% was greater than or equal to 4. So then this is where everything comes in. This was our dilemma. We need to find the probability that x is greater than or equal to 4. That is not in the form. So to rewrite it, we do 100% minus the probability that x is less than or equal to 3. And notice that it's 1 less. If you go up here, our dilemma was we were trying to find the probability that x is greater than or equal to 4. So we needed to find 4 plus 5 plus 6 plus 7. But if we want to do it in our calculator only does less than. And we can't put in 4 because if we put in less than or equal to 4, it's going to be 4 plus 3 plus 2 plus 1. We're going to be double counting this 4. That's why you need to do it 1 less. So the probability that x is greater than or equal to 4 in the discrete case is the same thing as the probability that x is less than or equal to 3. I really hope that makes sense. And I put it down here. For binomial CDF, we need the probability that x is less than or equal to x. Oh, sorry if I'm saying x twice. I usually put capital X and lowercase x. I should probably use different variables, but that's how it is in a lot of probability classes. And to list everything, you should probably take a screenshot of this. So for binom CDFs, to put it in your calculator, the probability that capital X is less than or equal to lowercase x is simply binom CDF, n, which is the amount of trials you're doing, p, which is the probability of a success, and x, which is the amount of successes you're looking for. So in our case, we shot the basketball 5 times. We're looking for how many times I make 2 shots. So that's going to be the amount of times I make 2 or less shots. That's going to be binom CDF 5 for the amount of trials I'm doing, 80% for the probability of a success, and 2 for the amount of successes I'm looking for. So next we have this is simple. We can simply get to the answer. But if they ask us, what is the probability that x is less than little x? Well, looking at the discrete graph, the probability that x is less than little x is the same thing as the probability that x is less than or equal to x minus 1. And this is in the form of binom CDF. And you could go ahead, put that in your calculator. And then this is where a lot of people had questions. The probability that x is greater than or equal to little x. If you look at the graph once more, it's going to be the same thing as 1 minus the probability that capital X is less than or equal to lowercase x minus 1. And that's simply 1 minus binom CDF np x minus 1. And same thing on the last one, probability that capital X is greater than lowercase x is the same thing as 1 minus the probability that capital X is less than or equal to lowercase x. You could take a screenshot of that, and I really hope this helps out. And that's it. Here's wow, I'm doing this on an iPad. It's terrible. Here's a discrete case, the entire thing, if you want to take the screenshot of it. I really hope this helps. And that's it.